Alright, so I want to introduce a concept here for integrating slightly more complex functions. And we're going to use a process called substitution. Alright? Now, I want to start with something we know how to do. Here we have sine of 2x. So sine of a linear function. You guys know that you can simply take the integral of the outer function sine, which is a negative cosine, and then we multiply by 1 over the derivative of the inside. Okay? And notice I even though it's always 1 over 2, I keep saying it's 1 over the derivative of the inside. And the reason for that is because that helps us understand a little better this process of substitution now that we've gotten here. Okay? I actually want to show you kind of the process that we would use here. What I'm going to do is I'm going to take this 2x, and because I have a function within a function, what I'm going to do is I'm going to rewrite this integral as the sine of u. Okay? Now, I still have a dx here, but what did I just make u equal?
2x.
Alright, I just made u equal 2x. Now watch this. This is where it's kind of interesting. What I'm going to do is I'm going to take the derivative with respect to x on both sides. Okay? So I have the derivative of u with respect to x equals the derivative of 2x with respect to x. Okay? Now watch this. This right here on the left-hand side, I could just rewrite as du dx. Right? Okay? Du dx. What is the derivative of 2x with respect to x?
2.
It'd be 2. Okay? So, if I wanted, I could say now, I'm going to multiply both sides by dx. And look what I have. I have du equals 2 times dx. Everyone follow what I just did here? This is a key step in this process. Now, why do I care about this? Look up here. When I substituted in a u, I'm still taking the integral with respect to x, aren't I? So, I can't integrate because I don't have any x's to integrate with respect to. Alright? What I need instead is I need to have a du so that I can integrate sine of u. Does that make sense? Alright? Now, really what I'm doing here is I'm deriving the rule that we've been using, and then we'll see how it applies to other functions as well. So, this is where we can tie together a little bit of what we did before when we were told, hey, consider the integral of this, or the derivative of this, and find the integral of this. We were kind of doing some of this in a very informal way. But I want you to think here, I don't have a du, I have a dx. But what do I know about du? Du equals 2 times dx, right? Do I have a 2 times dx? Do I have 2 times dx? No. So what? We got to multiply by 2. We need to make a 2 times dx. So that whole thing is du. That's what we found back here. Let me move this up so I don't have to keep going up and down. There we go. Okay? So since I have a 2dx now, I can replace that with a du. Okay? Am I allowed to just throw a 2 in there if I feel like it?
You have to multiply the outside by 1/2.
There we go. Multiply the outside by 1/2. Multiply the outside by 1/2. What's the integral of sine?
Negative cosine.
It's negative cosine. Okay? It's negative cosine. So now watch. I have 1/2 times a negative cosine. Well, I'm still in terms of u, right? Cosine of u. So now I'm going to substitute back in u equals 2x. I put the 2x back in. There's my final answer. Okay? That's really what's going on behind the scenes of this rule that we've been using. 1 over the constant, 1 over the derivative of the inside, times the integral of the outside. Okay? So that's why we call this u substitution. I'm taking that inner function, I'm replacing it with u, but then I have to figure out what du equals and make sure that I actually get that in here before I can integrate. Okay?
So then whenever the inner function is equal to, so if it was like the sine of 3x, then it'd be, you'd replace du would be equal to 3dx, and you put a 3 there instead?
Mm-hmm. Yeah. Here, let's say I'm taking the integral of 1 over, a 5x minus 1. Okay? I can let u equal 5x minus 1, right?
Okay.
So then I would have the integral of 1 over u, but it's still with respect to x. So now I need to figure out what du would equal. Alright? So du dx equals
5x minus 1dx.
the derivative of this with respect to
Oh,
x.
so 5dx.
So just 5. And then now I'm multiplying by the dx.
5dx.
Okay? Alright? So now I can substitute in. If I put a 5, so I have the 5 dx I need, I can replace that with a du. So now I'm taking the integral of 1 over u du. Okay? But I have to counter that 5 with a 1/5 on the outside. Okay?
Okay. And then you just plug it back in at this point.
Before we integrate, then we'll plug it back in. So what's the integral of 1 over u? ln of ln of u. Okay? And now we'll plug back in what u was. So 1/5 ln of 5x minus 1 plus c. Okay? Now, here's the thing. You guys know the rule we learned Monday. You're not going to do that when you have a linear function here. Okay? Unless you've just been totally lost and this makes a lot more sense. Then go ahead and do it. Alright? Where this is helpful, however, is when you have functions that are not linear functions inside of another function. Okay? Now, let's look at the rule in general here. Okay? This is equivalent to kind of a chain rule for integration. Alright? There isn't technically a chain rule, but it's kind of an equivalent idea. Alright? If u is a function of x, then f of u times du dx is going to equal the integral of f of u du. And notice here, the dx's would cancel out, right? That's how we end up with just du. Okay? The key here is, though, you've got to have a function with a function inside of it, and then you have to have the derivative of that function with respect to x. Okay? Now, let's start looking at one just with notation. Okay? Here, I'm going to let u equal some function g of x. Alright? So, du dx would be g prime. Alright, you guys know that. So, if I was trying to get du here, I would multiply both sides by dx, and I'd get du equals g prime of x dx. Okay? Now, let's say we have this function g of x that's being raised to a power r. Okay? But then I also, inside the integral, have the derivative of g of x times dx. Okay? Notice here, du, oh, I'm messing up my colors. Okay? Du is g prime of x dx. Well, there's g prime of x dx, so I replace it with du. Okay? Since I'm letting u equal g of x, I can replace this g of x with a u, and now I can use my power rule. Okay? So let's think this through. Let's say I have the integral of 2 times 2x minus 1 to the third power. Okay? Now, without using this, we would have to do, well, we could use the rule we learned Monday because this is a linear function. Alright? So we could make it 2 times the integral of 2x minus 1 cubed dx. And then how would I find the integral here? Of something cubed.
You just multiply 2 times.
What?
Or you just do like 2x minus 1 3 times.
We could FOIL the whole thing out, and then we'd have a polynomial and we could integrate each piece. Okay? I really don't want to do that.
So just put the line derivative outside, integral on the outside, times derivative inside.
Okay? There's the integral of the outside times 1 over 2. And then we have the times 2, so that cancels out. And this is what we're left with. Okay? Or, if we recognize, hey, I'm going to let u equal 2x minus 1. Alright? 2x minus 1. What is the derivative of 2x minus 1?
2.
It's 2. That's du dx, right? So du is going to be 2 times dx, right? So check it out. I already have a 2 and a dx in here, don't I?
Yeah.
So I could integrate this instead as u cubed du. Alright? This is the du. That's where the 2 went and the dx went. The 2x minus 1 is the u. Alright? So now we're thinking, what's the integral of something cubed? Well, it's something to the 4th over 4. And now we can substitute u back in. So it's 2x minus 1 to the 4th over 4. Same thing we got right here. Okay? So, that's the basic idea of u substitution. Okay? That's the idea of u substitution. We're going to do more of this on Thursday. Alright? But I want to do one other example here just to show you how this can work. This one's a little more complicated, so you may want to just not write it down at the moment and just kind of focus with me here on this. Alright? Here, unless you're looking for it, you're probably not going to really notice, oh hey, I could use u substitution. But, notice here I have this to the 4th power. I'm going to let that equal u. U equals x squared plus 3x. So I'm going to have the integral of u to the 4th something. Okay? I have 2x plus 3 dx left over still. Okay? What is the derivative of u with respect to x?
2x.
Ah, what do you know? If I multiply by dx, du equals 2x plus 3 times dx. That looks familiar, right? That is right here.
You have u to the 4th times du.
Exactly. I have u to the 4th du.
And then you substitute back in, right?
Well, we integrate first, then substitute back in. So this would be
u to the 5th over 5.
u to the 5th over 5.
du.
Well, the du is just there so we could integrate.
Then times 2.
Okay, so we have the 2x plus 3. I'm sorry, no, not the 2x plus 3. We need to substitute back in the u, which is an x squared plus 3x to the 5th over 5 plus c. Okay, so we just integrate this. Ignore the fact of where we came from at this point. Just keep it simple. What's the integral of u to the 4th? U to the 5th over 5. After you do that, then you're substituting back in what u was.
How come that first part is u, not the second part, like why?
That is just something that with experience you have to recognize.
Okay.
What to call u.
It's because it's linear.
Well, if you're thinking about the process, we know that the du is going to have to include the derivative of whatever you call u. So yeah, the higher power one is the one that, this is a squared one. When I differentiate that, I'll get a linear, so it makes sense to try this to be u. Now you'll run into ones that don't work, but that's kind of the idea of what you can do. Alright? Alright, so there's u substitution in a nutshell. We'll talk about it more on Thursday. We'll do some practice Thursday and Friday. Alright? So, we'll be good.
Next one.